Hi, I'm Dr. John Estes, and we are now talking about solutions to differential equations and trying to understand what a solution to a differential equation would look like. So, a solution to a differential equation is simply a function, but this function has to meet certain criterion, and so we will write that down just to explain what that looks like. So this function phi of x has to meet certain elements. First, there has to be an interval on which phi of x is defined. Secondly, the function and the appropriate amount of derivatives have to all be continuous on this interval. These first two steps are very important and often overlooked, but to really understand what a differential equation solution is, you have to have this interval specified with it. Thirdly, the function has to meet the identity of the equation. To illustrate the concept of solutions to differential equations, I'm going to look at a couple of examples. The first one being this first order linear differential equation that is dy dx minus 2xy equals 0. And I'm not going to show how to get a solution to this. Right now I just want to show what a solution looks like. And I claim that y equals e to the x squared power is a solution. Now remember, I just mentioned that you have to have an interval and you have to worry about continuity in these things. So since this is a first order, I need to consider the first derivative. So staying consistent with the notation that I have here, that's dy dx would be the derivative of ex squared, which is ex squared, times the derivative of the exponent, right? That's chain rule. So that'd be 2x. So we have 2x e to the x squared. Now, both of these guys are continuous on the all real numbers on negative infinity to positive infinity. So I can let that be my interval. The third thing I need to do though is make sure that it satisfies my equation here. So if I say the derivative of my function, which is the e to the x squared power, minus 2x times my function, which is e to the x squared power. Hopefully this equals 0. But if you can see my work, you'll see that 2x e to the x squared minus 2x e to the x squared power, of course that equals 0. So here we have a solution on the interval negative infinity to positive infinity. For my second example of a solution to differential equations, I'm going to look at this second order differential equation. And again, I'm not going to tell you how to solve these yet. We're just going to illustrate a solution. So here we have y e to the negative 2x, and I claim that this is a solution to this differential equation. Since this is second order, I'll need to consider two derivatives. So I take the first derivative of this, and that'll be negative 2 e to the negative 2x. Remember, you have to use chain rule in there. And then if I take the second derivative, so the derivative of this, we would get positive 4 e to the negative 2x. So now when I plug that back into my equation, and I have the second derivative of my function, plus 5 times the first derivative of my function, plus 6 times my function, I should get 0. And this, the function I claim works, is e to the negative 2x. And so if I just apply my derivatives that I've already worked out here in Scratch, I have 4 e to the negative 2x plus 5 times negative 2 e to the negative 2x plus 6 e to the negative 2x. And so if you notice, that's going to be 4, negative 10, and 6 adds up to give you 0. So here, y equals e to the negative 2x is a solution. On what interval? Well, this function is always continuous. So we can say on negative infinity to positive infinity would work. All right, now here's the thing though. I think there's another solution to this differential equation that's completely different from the one we just worked. So let's try this again, and this time I'm going to pick y equals e to the negative 3x. Now if I take the derivatives here, the first derivative would be negative 3 e to the negative 3x. The second derivative is 9 e to the negative 3x. If I plug it back into the original equation, I'm going to get a similar result. Watch, I'll have 9 e to the negative 3x plus 5 times negative 3 e to the negative 3x plus 6 times e to the negative 3x. And if you notice, that's going to be 9, negative 15, and 6. Those add up to be 0. So here we have a second solution. Y equals e to the negative 3x is a solution. And on what interval? Well, again, just like e to the negative 2x, these functions will be continuous everywhere. So we can specify on negative infinity to positive infinity. Now, I haven't shown the complete story behind these solutions. We've seen with the second order differential equation, we had two different solutions. With the first order, we only had one. I'm actually going to show, if we go back to this first order differential equation, and the solution we originally said was y equals e to the x squared power. That is true. We illustrated that, but we could also say that if I multiply this guy by any constant, I will also get a solution. So y equals 2 e to the x squared and y equals pi e to the x squared and so on will all give me solutions to this differential equation. For this reason, we consider e to the x squared power is a solution. If I multiply that by a constant, I generate a family of solutions. And since it only depends on one constant, we call that a one-parameter family of solutions. So we can actually have multiple solutions to the same differential equation, and we get this nice formulation of all of them right here. Now, if we consider the second differential equation that we looked at, the second order differential equation, we had two solutions. We had y equals e to the negative 2x, and we had y equals e to the negative 3x. And so in a similar fashion, I could multiply the first solution by a constant, let's call it c1, and the second one by, let's say, c2, and I get two different one-parameter family of solutions. The thing is, though, this may not be a good way to think about it, because actually, if you consider this, y equals c1 e to the negative 2x plus c2 e to the negative 3x. If you work out the derivatives on this and plug that back in the equation, for example, if you want, you can let c1 and c2 both be 1, and so you'd have y equals e to the negative 2x plus e to the negative 3x. You take these derivatives, add them up with these appropriate constants and such in this equation, you'll get 0 again. So here we've actually generated a new family of solutions that encompass all the solutions we've already found. And this is actually called a two-parameter family of solutions. So when you're solving differential equations, what kind of parameter family of solutions should you expect? Maybe it has something to do with the order. For example, when we had a first order differential equation, we only had one parameter family of solutions. When I jumped to a second order differential equation, I had a two parameter family of solutions. So there is a correlation with the degree of your differential equation. You'll have up to an n parameter family of solutions for an nth order degree. Next, we'll show you how to solve some of these equations depending on the type and classification. I appreciate you listening, and hopefully this has been helpful. If you have any questions, you can leave them in the comments or email me, and I'd like to respond. Thank you again.